Hey everybody, welcome back. Here we are, class 7 already. Tonight we're going to be talking about malware classification. This is kind of where we're going to start bringing all this stuff together. And, you know, there's a lot that is going to go on tonight, a lot of content. So we're going to move pretty quickly, but please try and stop me and ask questions. Hopefully I did a good job of explaining it. We're just going to skip kind of through the housekeeping stuff. Uh, Syllabus review, here we are. We're going to apply ML techniques to real threats. Um, this is links in with classes 2 to 4, ML fundamentals, scikit-learn, preprocessing. And this will also feed into incident response next class and adversarial AI in 13 and 14. So this will synthesize everything. Hopefully, everybody's been learning about ML and applying it to cybersecurity. This is on the path to adversarial machine learning. We'll talk some more about that. These are practical skills that are immediately applicable in careers today for cybersecurity. And this will also help you understand the black box, the pizza box that some vendors trying to sell your CISO right now. And you can ask intelligent questions and look really good when you're talking to their system engineer. Play stump the system engineer. Um, so, and this also feeds right into the capstone project. There's an assignment tonight. Uh, we're working towards capstone. This is a pretty substantial assignment, and it shows a progression from setup to pre-processing and feature engineering to model training, and that links into the final project. I thought about this, and I'm going to start supplying notebooks that are kind of a shell you can work from if you're stuck on a topic. I don't want anybody to be without examples. So for all the labs, I'll be doing a notebook in the future, and hopefully that'll help tie things together. Don't wait on this assignment though, because there's a lot to it, and you have to do some experimentation and make sure that you document your thinking process because you're going to come back to that and reference it in the capstone. So let's talk about what we're going to do today. Um, we're going to talk about static and dynamic analysis. So this is foundational for understanding feature extraction. Basically, every column is a feature. If you send all of your data, uh, from the logs right to your SIM or wherever, it's just too much, right? There's only certain features that are really important for identifying anomalies in machine learning, and we're going to talk about how we get to that. And uh, this is also important because if you think about pipelines, if you're going to do an ML pipeline, you don't want to just shove everything down its throat. You want to understand the data feeds and what you're looking for and curate that some, right? So you only want the important features. You want to make sure that data is pre-processed and it's scaled, right? So that it is something that a machine learning algorithm can use. And you also want to make sure that you do feature encoding, right? ML algorithms don't like text, but the flip side of that, right, is you have to be able to kind of reverse engineer that encoding. So if you're looking for a particular instance that belongs to a file or a host, you want to be able to figure out what that encoded value relates back to. Uh, then we're going to talk about feature extraction from malware samples. Uh, this is hands-on work with the Capstone data set. Capstone data set, we'll talk about that in a little bit. It's kind of we're stacking the deck in our favor. That has some implications. That's kind of why I went back and forth on the lesson guides today. I'll talk about that a little bit more as we move on. We'll talk about how to identify patterns that distinguish malware from benign files and feature engineering techniques. So the third part of this, right, is we're going to build and evaluate classification models. This is a practical implementation from scikit-learn. We're going to talk about random forest, gradient boosting, SVM, logistic regression. The only one of these we haven't touched on so far is gradient boosting, and I'll tell you why as we go along. Um, Interpret the results with cybersecurity context. And, this is kind of a small example, but we do get good results. In this particular example I put together, we get 99 plus percent accuracy. Um, so if you're going to follow along in your Jupyter notebook, make sure you have that running and you have the malware data set accessible, and we'll kind of go through it from there. And hopefully after the session, you'll be able to get a malware classifier working and you'll understand why certain features are predictive, right? Not all features matter. And we can tune models. Remember, we talked about hyperparameters, right? How do you tune hyperparameters? We're going to touch on that too. So let's talk about the foundational concepts that make machine learning effective for malware detection. All right. So what's malware? It's malicious software, right? The name mal means bad. Uh, there's many types: ransomware, banking trojans, APT tools, right? And they evolve in sophistication, right? AI is generating malware. You can go on the dark web right now and you can actually buy timeshare on a malware server. Don't ask me how I know these things. And there's fileless attacks, supply chain compromises. Supply chain is huge. I'm sure almost every company in the world uses open source software, whether they like it or not. I could tell you some interesting horror stories from Amazon and Project Kuiper, but I think I have an NDA that keeps me from doing that. But there is a lot of interesting things that pop up if you don't have a handle on open source. And the current threat landscape is 500,000 about-ish new malware samples daily. AV Test Institute says. So it's a huge growing problem, right? Um, Malware is polymorphic, it adapts, and that's what we have to contend with today. So the previous, kind of direction that things were going with signatures doesn't work anymore. So we have to figure out a better way. Okay, the question is, there's no notebook for lesson 7 in GitHub. Where is it? Uh, Look in the chat. I actually put it in the chat. I don't think I uploaded it to GitHub, Michael. Um, okay, so why does classification matter, right? From a business perspective, right? We need to understand behavior. Different families require different response strategies. We need to develop defenses, right? Targeted countermeasures save resources and improve effectiveness. The analogy I like to use is the amount of time, money, and effort that you can put into cybersecurity is like a jar of peanut butter, and you have a giant slice of bread. So do you want to put the peanut butter on thick in one place, or do you want to spread it over the entire giant piece of bread that's as big as Seattle? Right? So you're going to have a 1 micron thick layer of peanut butter. So you need to figure out where to concentrate your efforts. I mean, this is part of what we've been doing with zero trust and things like that. So, reducing attack surface and focusing our effort is super important here. Um, Threat intelligence. Everybody here has probably seen bad threat intel. You see the newsletter that talks about threats, or it sends you to a website, or you go to your threat intel platform and you look at some web page, right? How is that helping you as a hunter, as a defender? It's not, right? Unless it's in context with actual activity that's happening. Threat intel is not particularly useful. We'll talk about this some more. And then automated response, right? Wouldn't it be great if something was detected and there was some action taken before a human got to it? This is how we kind of close the loop. We respond faster. Companies that are embracing an AI reduce response from hundreds of days to hours. So, we'll see a little bit about how that fits into it. And in the context of industry, right? Average enterprise processes 100,000 files daily or more, right? If you're going to do manual analysis, 30 to 60 minutes per sample, that's pretty large, right? You're just looking at the features from one PE file and trying to figure out if it's malware or not. Or you're detonating it, right? Doing dynamic analysis. We can discuss that a little bit more as well. And uh, in ML, right, you can classify it as malware, not malware in less than a second. So uh, industry says, right, you're saving over $2 million in average breach with ML. I don't know how you measure that, but that's what the statistics is. So, we hear about new malware families all the time. Uh, you know, why don't we just block all unknown files? Can't do that, right? And there's news every day about malware campaigns if you look for it. So, if you look at traditional signature-based detection, it's less than 5% effective against new threats, right? Unless we know about it and we have a signature, it's not doing us any good. Uh, Behavioral analysis catches about 60% of unknown threats. And ML approaches 95% detection of unknown malware families, right? Because of its ability to cluster. And also, we talked about SVM, it's normal or it's not normal, right? These are all ways that we can identify anomalies and things like malware. So to build models, we need to understand how analysts traditionally examine suspicious files, right? So there's really kind of 2 points. Uh, One is we have static analysis. Technique. We're going to be looking at some of these. We have PE header analysis, right? We can see machine type, timestamps, entry points, that kind of stuff. Look at strings, right? If you've ever looked at PS tools and looked at strings in Windows PE files, right? You've seen this before, right? There's all different kinds of interesting strings in there. You can see URLs, IP addresses, reg keys, API names. Um, there's a lot going on. Uh, what functions does a malware use, right? That's import table. Um, Look at each section, code versus data. Does it have unusual permissions, right? Sometimes if uh, this was a classic back in the day where someone would subvert a Windows utility and that had high permissions and would abuse that, right? So those are good things to look at. And crypto hashes, file fingerprinting, variant tracking, right? Is this MD5, is the hash value correct? Is it signed? Those are all things we can look for. Uh, with respect to static analysis limitations, right? Um, Greater than 80% of malware uses obfuscation, right? Which means that I'm trying to make my code relatively invisible to you from a static analysis perspective. Uh, we used to have this technology at Microsoft called Warbird where we would do this. I don't know what they're doing anymore around that, but we would try and obfuscate the code. Wasn't very useful if you ask security researchers. Um, Polymorphism, each family looks different each time it executes. So that helps evade signatures. Um, you know, um, if you've ever heard of a term called code caves, right? There's hidden functionality in unused file sections. It's like, again, back in the day, the old NOP sled, right? I'm going to put a bunch of NOPs in until I overrun a buffer and try and find some executable code. Anti-analysis, you deliberately corrupt headers and structures, right? So it looks like a malformed file and it's hard to analyze, right? Because if you don't know what that structure is, maybe the malware does, you don't, it's kind of a guessing game. So then we come to dynamic analysis. This is controlled execution in an isolated environment. It's behavioral observation. You've heard of sandboxing before. Um, there's automated analysis in sandboxes. Things like Cuckoo, Joe Sandbox are a couple of solutions that you can do this with. It reveals the actual malicious actions, regardless of obfuscation, right? You can't tell looking at it from a static perspective what it's going to do, but if you execute it, you sure do know now. Um, uh, and then the temporal aspects, right? Is it time delayed activation? Is there a trigger condition? How does this malware get executed? Um, so dynamic analysis technique, you're looking at API calls. Um, you're looking at network traffic, right? Command and control communications, data exfil, uh, easy to detect, right? Maybe the malware executing itself is obfuscated isn't, but it's going to phone home. So you should be able to pick that up. File system, does it create, modify, encrypt files, right? You know what the normal file structure looks like. Data usually lives somewhere else. If your landscape of your installed operating system and program changes, machine learning is a good way to figure that out, right? We found something that's not normal. What is that? We're going to highlight it. And you can also look at registries in Windows, right? Uh, for persistence mechanisms, configuration changes. These are always fun, right? An oldie but a goodie is, having a scheduled process kick off that would, phone home or reinstall a process, do those kinds of fun things. Um, so, you need to look for those things and memory, right? Is there process injection, privilege escalation? There are better protections today now against these kinds of things, but there's always an exception. A big question was always, should we let um, antivirus and anti-malware vendors hook the kernel, right? Things like CrowdStrike, what have you. It can hook the kernel and it has high privileges. If it's subverted, as we know from some recent attacks here in the past couple of years, that can cause a lot of problems. Or if somebody does something dumb at CrowdStrike and they crater your machine. So again, it's a balancing act. You probably want that protection, but there is a potential cost to it. And then dynamic analysis limitations takes a long time, right? 5 minutes if you're good, 30 minutes maybe. You have to have the infrastructure, even if you have the magic box that detonates all the malware and all the files and things like that. It's not free. Uh, there is a lot of sophisticated malware that can detect sandboxes, being instantiated in a virtual machine, those kinds of things that won't run the payload. So you have to contend with that. And, it may not detonate completely under analysis conditions, right? If it partially executes and it detects that it is in a non-permissive environment, it won't completely execute. So you may not be able to get all the information out of it. So what's the trade-off, right? Static analysis is fast, dynamic is slow. Static is safe, dynamic isn't that much. You need a sandbox somewhere. Obfuscation in static is it defeats static analysis, bypasses it in dynamic. Static, you infer behavior, you don't actually see it happen. Dynamic, you observe. Static, you can scale it unlimited. Dynamics resource bound because you're actually executing, right? Low cost static, high cost dynamic, which means a lot of stuff is static. So you need to think about, right, when is static analysis sufficient, uh, or when is it not, right? How can the malware authors evade each approach? There's a lot of information out there if you go look. And what kind of combination strategy would be most effective? Maybe the first time I see this file, I go and I detonate it and I try and figure out what it is, and then I add it to my own internal, um, list of potential malware, and then I act accordingly. So, and then how does this connect with ML, right? Uh, Static features, right, are a structure and dynamic is behavior. You can measure both of those if you are trying to do analysis. You can take an ensemble approach and combine predictions from both types. And then with a real-time pipeline, you can do static screening to dynamic confirmation if the static screening suspects something is malware. So let's talk about how we extract meaningful patterns from both analysis approaches. And then we're going to talk about creating features for machine learning. Okay. So feature extraction, right? There's some code in your Jupyter notebook for this. Um, we have example here in lab 3. I'll post this up in GitHub if I haven't done it as well, right? And these are things here where we're going to be actually doing this work. So we load the data. We're going to do some basic data analysis. Uh, we're going to look at suspicious features, those kinds of things. And what this is going to do is it's going to give us a view of this particular malware sample that we're working with as to what it looks like, right? So our file has 19,611 samples, which is significant. It's not super huge, right? I was trying to do this with a bigger file and it didn't give me the results I wanted, so I had to roll back. Um, this is it's not a normal distribution. It's kind of inverse for training ML, right? It's 74% malware and 25% benign. It would probably be 95% benign or 99% benign and 1% malware in the real world, but we're trying to train a model here. Features, we have 69 that are extracted from the file analysis. And the source, this is a collection of files from VirusTotal, malware repositories, clean software that were all munged together for this particular data set. This is a publicly available data set. You can find it on Kaggle, you can find it on GitHub. A lot of experiments use this, so it's pretty well known. So with respect to the class balance, right? We talked about class imbalance. It's more malware than not. This lets us do some analysis and see some results that you wouldn't normally see, which is why I switched over again from my previous one that I published because I don't think it really illustrated the concepts as well. And we talked about it being, the inverse of an enterprise environment. You're going to have a lot less malware, right? If you're going to train an agent and you have labeled samples, you can construct your own data set so it is malware heavy. It's easier to train your algorithms. So consider that. It's probably biased towards predicting malware, which is why we have the high F1 score and the high accuracy, because we've kind of supercharged it in the training and test set. There's going to be more malware in a real world environment. You would probably want the inverse data set as far as testing and see how things went. But, consider that as you work through this. And so the files structure says some things about the malware that, malware is smaller sometimes, which is evasion or larger packed, right? So it's outside the norm. A couple things it found were that, unusual section counts indicate manipulation. We'll look at that in a visual. Non-standard entry points, as far as the addresses, suggest packing. That's one class SVM. We'll find that again. It puts a boundary around what's normal and anything else it considers an anomaly. And then, with respect to the image-based memory loading address anomalies, and again, you don't need to know all this. This is not a class on malware, but we're just kind of talking about some of the things that we found, right? We looked at the import-export analysis, right? Libraries, functions, imports, suspicious APIs. Those all can trend towards anomalies. Strings and metadata, right? This is, we'll look at this later with NLP, but this is the text, what's going on in there. This can provide us with some valuable information and, dynamic features like API calls, network behavior, does it phone home, file system, what's it writing, what's it reading, and then process behavior. So there's a whole bunch of this, right? And so if you, I guess the next thing we want to talk about is feature engineering, right? What does that mean, right? There's raw features, right? So that's what's in the file. If I look at this is our data set malwares. These are the raw features, right? So this is what came with the data set. Actually, if I look at this, I can see that it has been processed already. So this has probably been um, run through, and uh, this is typical of malware analysis, right? They take these files and pre-process them and give them to us. So we have a bunch of features that look like they've been normalized. And then the next thing is, right, we're going to do uh, some, use our brain as we look at this. This is another interesting thing. I'll talk about it when we get there. But when I was looking at this example, there's something that didn't make sense, right? And I had to actually go in and change some of the code around so it looked correctly, but it had inverted a couple things when it was doing the display. So we'll talk about that. And we're going to do normalization and scaling. Why do we scale? We scale so everything is standard deviations from the mean, so it's easier for algorithms to train. And we also don't want a bunch of text stuff in there. We want to encode it. And the thing you want to do about that is maintain interpretability, right? So you can explain it, so you can actually go back to the data and talk to somebody about what it means. That's super important. I know you've heard me mention that a couple of times, but you have to go and look at the data and understand what it means, at least so you can have a conversation. So that's a function of what we want to do with explainable AI, right? People don't believe AI unless you can explain it. So you need to be able to take care of that. And then, uh, so let's talk about the actual patterns in our malware data set. And this is a visualization that is from the notebook. So this is what I was talking about with respect to the data set distribution. I was looking at this, and before I went in and tweaked the code, it had the benign and malware reversed and the colors wrong, right? So to me, it looked like, I was like, oh, that looks like a normal data set, and it's not a normal data set. So what's wrong? So I went in and took a look at it, right? So this top left is the data set distribution. This is an imbalanced class. This is not normal. We have excessive representation from malware over benign, which is not usual, but for the purposes of this demonstration, this course, we're doing this so we get quite evident results, right? So one thing you'll probably see is we have high recall. We've seen that before. As everything looks great. Area under the curve looks fantastic, but it potentially lower precision, right? So we're gonna probably find more malware, but it probably would not perform as well if we had a larger sample set. So this is research oriented because a typical enterprise we see 1 to 5% malware. 5% is probably pretty aggressive. So the next box plot is number of sections, right? This shows some malware patterns, right? 0 is benign, 1 is malware. If you look at this line in the middle of this box, right, that's the median. So you can kind of get a feel for what the composition of the data set is. Again, this is kind of small, so it's a little hard to see. Uh, let's see if I can zoom in. I guess I can't. But anyways, oops, sorry. And it this is again an indication. You can see there's a clear difference between malware, uh, between benign and malware, right? 0 is benign, 1 is malware. So you see there's some differences, right? Our algorithm is going to pick that up. Um, if you look at the image size distribution, um, it has a log scale because it's a wide range. This is not probably as exciting, but again, you can see there's a clear difference between um, malware and benign. If I was just looking at one feature, I probably couldn't pick this out. But again, if I'm using an ML algorithm, it's going to figure out what features are important and look at the multiples of these. Same with the other ones, right? Entry point address distribution, different ranges, different distributions. You can see here, this is kind of interesting, right? With malware, it has suspicious imports are high, and also this little teeny tiny block has suspicious names, but that is another indicator, perhaps, that it is malware. And you can look at all these and you can see that there are clear differences. But could you pick out from one feature in one sample and decide if it's malware? Probably not, right? So, we look at our feature correlation. This tells us, right, what features um, that when paired together have a high degree of variation or variance, right? Where they've got features that are a large distance from the mean, and together maybe they're an indicator of malware, right? So this feature correlation is how we try and pick our features, right? As far as feature importance, right? We have this top 15 features by correlation town here directly underneath it. So this tells us what features we would probably want to look at, right? As we build a pipeline. Um, then we have our malware samples by year. This is kind of interesting. It sort of shows you the peaks and valleys with respect to this. This is an older data set, as you can see, so we don't have any recent data. This is from a couple of years ago. Things like import table size and all these different things together, right, is what our algorithms use to help determine what is malware and what's not. And correlation doesn't mean causation. Um, outlier it, Outliers are significant, right? They can either be a potential evasion attempt, or they could be a quality issue. And then we still have some overlap of features between classes. All right. So now we're going to talk about building a classification, right? This is where we get to the point where we're going to actually use an ML model to try and classify. Um, so as you know, we always do data pre-processing. And this is what the previous homework and labs we've talked about. We do missing value handling. We scale our features. We encode our categorical features. We don't need it for this PE file because it's already numeric. But real world data is messy, and pre-processing ensures that we have a stable model. Um, so a couple of the algorithms we're going to talk about. One that we didn't talk about is gradient boosting. Um, this is an ensemble method inside of scikit-learn. The The power of this is that it's designed for structured features that does tabular data really well. So things like PE files. Um, it has missing value handling, right? So you don't have to do an imputer to handle missing values and clean it up. Um, it automatically discovers the complex relationships between features. Um, it has the ability to not overfit, right? Which means that it would over-index on some particular features. We talked about that. The curse of dimensionality. If you do binary encoding, you can have so many features it makes it hard to train the model. Um, so so it's excellent for malware detection because it's optimized for large data sets. So with boosting, we want to start simple, train a basic model, find mistakes, and then train another model to fix the first model's mistakes. So it's an iterative process, and you continue that until your performance plateaus. And we've talked about that a little bit with like the elbow method. And it's like having a team of specialists where each expert focuses on fixing the previous expert's mistakes. Um, so other algorithms we've talked about is random forest, right? This is ensemble of trees, right? Many decision trees, the yes, no decision matrix, like we talked about in one of the first lessons. Um, so it trains them in parallel, right? So each tree theoretically, well, I guess not theoretically, it says they're trained on a different data subset. I don't know how you prove that or not prove that. I guess we have to trust the algorithm writers. Um, it does a final prediction by majority vote, kind of like a Monte Carlo simulation. And it's robust and less prone to overfitting, right? Because because it's a tree structure, it finds the outliers first, and then it hones in on what kind of is normal. And this is good because it gives you a good baseline, and this will also give you feature importance. SVM, we talked about this before, right? This finds a margin, right? The optimal decision boundary. Um, and that's, if anybody ever asks you what the decision boundary is, it's the margin. And the plus minus from the margin is kind of how sensitive it is to uh, the particular value, right? Is it in? Is it out? Is it on the boundary? Uh, that's an important term to remember. Uh, it works well with many features, right? It finds what's normal. It's flexible. And the challenge is, right, you have to scale the features and it's sensitive to parameters. The hyperparameter tuning of SVM can make the difference between something running for hours or days or running in minutes. So you have to play around with that a little bit. Logistic regression, we looked at that, right? That's the line going up to the right. It's simple. A lot of people are able to interpret that and make sense to them. It has a natural probability. We use this for area under the curve, right? Greater than 50%, it's better than a guess. Um, it's quick to train and predict. But the limitation is it assumes everything's linear. So, all right. And then we've talked about data splitting. Remember, important 80% train, 20% test. Do not train your model with your test data. Keep the two separate. Otherwise, you're going to have issues with it overfitting, right? Because it's going to know all the answers already, which is good, I guess, if you're taking a test, but it's bad if you're an ML algorithm. And you know, you if you do train test split in a scikit-learn, theoretically should give you a balanced data set. I've actually never gone and looked at that. That might be an interesting experiment to see, if your X test to X train have similar ratios by looking at them. But I didn't do that for this class, but it might be something you'd want to look into. And this is critical, right, for imbalanced data sets like ours, because of the fact that it would be easy for it to guess because of the prevalence of malware, 75% almost. So, um, we talk about model training and selection. Um, you need to think about performance. How accurately does it classify? Speed, can it process it quickly enough for real-time use, right? This is a big issue. If you're, this is like my IDS example from a couple classes ago, is if you have too many things that it's trying to do you have enough horsepower for it to process the stream in real time? You have to think about that. And uh, can the interpretability, can your analysts understand the decisions? And is it robust, right? What does it do if it comes up against something it's never seen before? How does it handle that? So you need to think about which algorithm performs best and why. What are the trade-offs between accuracy and speed? And then how do you explain it, right? Is it explainable to someone who is not a security ML person? Do you understand it well enough to explain it? So let's take a look at how these different algorithms performed on our malware detection. Okay, so these are results from actually running the models in our example notebook. Um, and this is the actual output. So you can see the different sections here. I'll post this notebook, right? It talks about feature engineering, pre-processing, feature selection, model training. It's
Can
all
you
in there.
increase the font size, please? Thank you.
Yeah, can do. Sorry. How's that? Okay. Um, and we compare the performance of the different models. Uh, we look at the ROC curves, right? Remember the area under the curve, this line is 50%. If it's greater than 50%, it's better than guessing. If it looks like a shape and it's less than 50%, you may have to do more feature engineering or some more training. Uh, Random forest tells us which features it thinks are most important. So it gives us kind of the top 15, right? So when we do dimensionality reduction, we'll only be looking at less features. This is important if you're building a pipeline. Um, we talk about our confusion matrix. This is scary good, which means I don't believe it. If it's too good or it's too bad, there's probably something wrong. So you need to go back and look at it. This looks this way because of the fact that we have a preponderance of malware in the data set that we used for this. So I'm not surprised by this. But if this was a normal sample of PE files, I would be suspicious. So I did a different take on this with a larger file that looked like more of a normal distribution. I'm not going to go into that right now, but I will post the file up in GitHub along with the data. But it looks different, right? And then the prediction probability distribution, it's based. You can see looking at the confusion matrix, it's super accurate, and that's sort of what this represents. All of these small bars that you can barely see between the two large red and green bars are um, are different suggestions, but you can see that we get almost 100%, and then we've got a small percentage of wrong predictions, and this is pretty good. And then we talk about the performance summary, right? Accuracy is 99%. Uh, Precision is 99%, recall is 97%. We have a high F1 score for malware and benign. This is super good, right? This is better than anything that everybody has ever sold, which means it's probably bogus because of our file structure, But if you tried this on a larger set of files, you would probably get a different result. And these numbers would probably change, but this does say it's a fairly robust model. The thing I'd be worried about with this is that it's overfitted. Okay. So let's talk a little bit about the model training. So this is the model fit method. This is where you train your model when you do model fit. This is a core concept. And this is really super important because this is where the machine learning actually occurs, right? You need your training features, right? X train, Y train from your split. And the output is a trained model that's ready for prediction. So the metaphor is you teach somebody with thousands of examples and answer keys, right? So the the detailed process is so let's not look at code, sorry. But you start with the the model, right? And it examines the relationship between the features and the malware labels, right? So because it's looking at labels, this is supervised learning, right? And by because of the fact that if you look at the data here, there is a malware column, and this is what it's based on. If you just, and you can see why this would be impossible if you're just trying to look through this, but you can find the malware column, the malware feature, and that's what tells you what each one of these is. So it's labeled somewhere,
Was
but
BA. I
hmm?
think it was column BA,
Yeah, thanks.
or right there.
All right. Yep, BB. All right, cool. But you can see, right, this indicates which of these files are malware. And it looks at the features, and you can see that there are some features that are duplicate throughout here. These features a lot of times will get cut by feature importance, and it gets it down to a set of like that top 15 features we talked about. And that's what it helps determine what's malware and what's not. And you can also look at the correlation matrix that we looked at earlier, and that will tell you as well. So if there's a high correlation between features and the indicator of the label of malware, your your model is going to know what characteristics of those features help determine whether it marks it as malware or not, right? And again, I like using SVM as an example because it has a boundary. The boundary is pretty clear. If you look at a lot of the other algorithms, logistics regression and some of the others, they have a clear boundary as well. And that's how we help determine that is the combination of all those different features together. And the relationship between them and the label is how we train our models. Okay. All right, I see a couple of people said the notebook doesn't work. Let me check on that after class and see what happened. Um, so I've got open here. So maybe there's something happened with the upload. So if I apologize about that. Okay. So so the model is going to examine the relationships, identify the combinations that indicate malware. And an example might be like high entropy and missing version info and unusual imports is likely malware. And when we talk about those features and the characteristics, we're talking, because this has been scaled, we're talking about the number of standard deviations away from the mean that is are probably those indicators. So remember that it's not the ordinal value associated with it you see in the sheet. It is the scaled relationship. If you are interested, you can go look at that. You can look at those data frames in the notebook if you want. You can just print them, or what have you, but they're there so you can kind of see what that looks like. Then we're going to optimize parameters, right? So different algorithms, I'm sorry, use different strategies. We talked about random forest building a bunch of decision trees, and each tree learns a different aspect of the malware pattern, and you combine those for robust predictions. Gradient boosting, right, is a simple model that's maybe just an average prediction, and it can identify the samples that are not classified and train a new model to fix them, right? So gradient boosting, right, it iterates and improves itself. There's different kinds of gradient boosters. They take a long time to run on scikit. Uh, for this, I used his gradient booster because it runs faster, but just normal gradient booster, it can run for hours and hours. But play with those and see. The claim is his gradient booster is just as good. Um, I don't know if there's a difference or not. I can't really tell. Then the next step that it takes is it does a thing called loss function minimization. So it tries to minimize the classification errors on training data, so it knows, because it's training data and it has a label, what is and what isn't actually malware, and it tries to resolve some of the issues. And this means that we don't want to memorize things, which is called overfitting, or oversimplifying, which is called underfitting. So this stops when the performance plateaus or it reaches what's called a maximum iteration, right? So which is a hyperparameter that you can set. So then the model validates, right? It does internal validation by cross-validation during training. Um, you can tune the hyperparameters. We'll talk about that a little bit. This is to optimize algorithm specific settings. Remember, we talked about K and new a couple lessons back, right? Those are examples of hyperparameters that you would tune, and then your model is going to be ready to deploy, right? So there's a bunch of details with respect to the individual algorithms, and then like random forest training and gradient booster training, they go through this process as well. And then at the end, the model learns the feature importance patterns. We talked about that. What are the structural indicators and behavioral signatures that indicate malicious file capability? And then characteristics of packed or obfuscated files for evasion detection. And so, some of the challenges of training, we talked about overfitting, um, right, where it learns too well, I guess, uh, because of the fact that you're feeding it. So this would be an example of where it might find all the malware, but it might miss things that are close to the edge, right? Because all we did was train with malware. So this specific model, I would be suspicious that it might be overfit because of the fact that we fed it an inordinately high number of malware samples, but we're doing it just for the standpoint of getting a good result. So this is like I guess it's like training a doctor with thousands of patient cases and outcomes. Doctors really are statisticians. I never understood this till I had a long talk with a physician one time, where they go by the percentages. They look at the symptoms and they say, oh, 80% of the people that had these symptoms had this problem and they give them this medicine. Same kind of strategy here. Or people can learn faces by studying many photos. If if you're looking for someone or you are trying to track somebody down, you can use this kind of strategy. Um, or the chess analogy, if I analyze millions of games of chess, I would learn some useful strategies. So the model doesn't memorize training data, right? It's looking for patterns. Complex isn't always better. The best models are complexity and balance between complexity and sort of generalization ability. You want to have a model that's good enough, but it doesn't have to be perfect. And training doesn't happen instantly. It depends on the data size, the complexity of the algorithm, and how much computing you have. So start simple, monitor progress, validate it thoroughly, and then track what you're doing with hyperparameters and the results for reproducibility. So that was a lot, but that's an overview of how models learn. And so let's talk about some of the features we found in our analysis for malware detection. So, so this is kind of a statistical view of our PE file, our malware sample that we're going to use for our capstone. So on the left here, we have the top 15 features by correlation. This is a ranking system. The features are ordered by the absolute correlation with malware classification. You can see the obvious one that's 100% is malware. If I was going to spend some time tuning this, I would make it so that that wasn't considered as part of this, but it is actually considered. So, it's valid to have it on this chart. Uh, you know, we talk about different things like, if you look at the correlation values, there are some that are higher than others. And things like linker version, malware uses different compilation tools probably than get used at Microsoft or some other company. File structure, remember, files are standard except when they're not. So if I have an anomalous file structure, it's potentially malware. Uh, we have like alignment, right, which is the difference between malware and legitimate software. DLL characteristics, runtime flags, right? So something different is going on when I execute malware. And then, section alignment, memory layout patterns can indicate malicious intent, right? If I don't line up, if I don't play nice in the memory space, there's probably something that I'm interested in. Okay, so I'm not going to go into depth on all these features, but I did want to talk about the correlation pattern analysis, right? If it's red, there's high correlation. You can see these ones that are one, it's correlating with itself, but all these other ones that, sorry, I don't know why that does that, but all these other ones, like if it's blue, it's low. If it's red, it's high. So the ones that are orange, if you went through and connected the dots on these, you would probably see some of these top 15 features in there. So that's kind of how it picks it out. Remember, at least in this particular case, the high is red and the low is blue, so hot to cold. And you can see that obviously as it goes towards one, it's a strong relationship. Anything higher than 0.8 is good. As it goes down, anything less than 0.5, again, it's kind of like guessing. So, high correlation pairs, you can potentially benefit from feature engineering, right? You could create a new feature of that kind of ratio. You could say major link inversion and minor link inversion is a compiler score. So just some thoughts there. Use your domain knowledge to combine features based on your understanding of cybersecurity, right? If you have high entropy and missing version, it's suspicious, and figure out things that are nonlinear, right? That are complex. And from a standpoint of the model performance, uh, if you were selecting the features that you were going to use in your model, you'd want to make sure that they have this high correlation, that there isn't redundancy, right? If you have features that are kind of intercorrelated, maybe you need to do some feature engineering. Uh, Make sure they make sense, right? Explainability and interpretability. You have to be able to explain what's going on here. If you just show up with a bunch of eye candy and you can't explain it, it's going to be hard to get people on your side. And you know the and this is really, again, up to your professional intuition. So this is kind of the correlation insights that help guide the feature selection. And you need proper metrics, though, to assess the model performance in the cybersecurity context. So that's what we're going to talk about next. Okay, so remember we've talked about precision and recall, right? These are the two most important things probably, and F1 score. So precision, as a reminder, answers of all the positive predictions the model made, how many were correct? And then recall answers the question of all the positive cases, how many did the model correctly identify, right? So it's correct, and then how precise were we? Which is kind of backwards. And then um, so the trade-off, right, is you can improve one at the expense of the other, right? You can have higher precision and low recall. So that can mean your model is very careful about making positive predictions. So if it predicts, it's usually right, but it might miss some actual positive cases, right? I think that's a type 2 error, if I remember right, which is bad. Or you could have high recall and lower precision, and it catches most of the positive cases, but includes false positives, right? This can lead to alert fatigue and things like that, right? I'm sure everybody at some point in their career, if you're not doing it now, you have to sort through the false positives and decide what actually is applicable or not, right? That wastes a lot of human effort. So you need to figure out, right? The trade-off is, again, that do you want to catch only things that are positive and not have any false positives, or do you want to spread the net a little bit wider, right? The margin is greater, and have false negatives and potentially some analyst effort, right? So you need to make that decision. So real world might be a spam classifier. High precision would mean that few legitimate emails get marked as spam, but some spam might slip through. I think this is kind of how most uh, spam classifiers work, because everybody gets a few spam mails. And then high recall would mean most spam gets caught, but some legitimate emails might get marked as spam. I don't know about you. Everybody at some time probably looked in their spam folder and says, "Oh darn, I was wondering where that went," or "Hey, that really is important. My uncle, the Nigerian prince, wants to give me some money," but you need to be aware of these things. And then we talked about F1 score, which is the combination of the both. And that's a single metric that balances both precision and recall. And that's useful when you need to optimize for both simultaneously. And the choice is up to you, depends on your use case. So um, the key thing is, right, we talked about the prediction process. This is binary classification, because want something is malware or it's not malware. There's not a bunch of different cases, right? So we would have two clusters, right? We would have a cluster malware, we would have a cluster not malware. And with respect to evaluating it, right? we look at our result in the lab and it's 99% accuracy. That sounds good, but that's misleading probably because our data is imbalanced, right? So it's just going to find the majority class, right? So accuracy isn't sufficient for security applications. You need to make sure that you take into account precision and recall and F1 score. Confusion matrix, right? That tells you the truth. We've talked about this before, right? How good is the model actually working? And then, if you look at our confusion matrix, the results are pretty good. We have, our 974 true negatives, 29 false positives, and pull up the confusion matrix. Sorry. So there's our confusion matrix, right? So it is correctly identifying, benign files and the actual malware files. And this, if you looked at this, if this wasn't a kind of an imbalanced data set, you'd say, wow, this thing works really, really good. Then, we talked about precision, right? That's our quality of positive predictions. It's, the question from a business perspective is, of all the files we flag as malware, what percentage actually are malware? So high precision, again, fewer false alarms, less user frustration, less analyst impact, and this reduces analyst workload. And that might be fine, right? It is, if we can dial back and reduce analyst fatigue, are we in a worse spot necessarily? That's a good business question. Recall is, of all malware, what percentage do we catch? And if you have high recall, there's fewer things that slip through and better security, and this prevents breaches, right? So what does this all mean? Right? False positives have costs, right? So for the 29 benign files we flag, potentially block somebody from legitimate software or websites. There might be a help desk ticket. There might be an investigation. Might be a delayed workflow, right? What if somebody can't do their work because they are in no man's land because they've been blocked? The users are going to complain, which comes back to you ultimately. And it has a cost, right? How much does it cost? Does it cost $50? Does it cost $200? Depends on who you talk to, but it's not free. If you're blocking a critical business process and you miss a deal because of it, right? Could have a lot of potential cost. So we missed 6 malware files. What's the cost of that? Potential infection data breach. If we do get compromised, we have the bad guy inside the wire. We could have lateral movement, spread malware throughout the network. What if they're exfiltrating data? That's an issue. Is it your company data? Is it user data? Right? There's all kinds of horrible things that go on. The recovery cost, right? You got to do incident response. You got to rebuild the system. You got legal fees. You have investigations. You have a bunch of stuff associated with it. This is expensive. Industry average is 50 grand to 2.4 million per attack, right? That's a pretty broad range. Things can go bad in a hurry. So you need to think about this. So your false positive cost at the end of the day, your false positive cost is less, right? If you figure our 29 false positives cost $100 each, that's 3 grand ish. And let's just say the false negatives cost 100 grand each. That's $600,000. So that's something to keep in mind, right? That it might be better to have a little bit more analyst toil on the front end as opposed to missing something that is potentially malicious. All right. Okay, so hyperparameter tuning, when we ran the lab, we have code in here to tune for hyperparameters, right? It's up in here. It helps us find the best model, and it's looking for the best AUC score. And Mike, I'll answer your question. I see it in chat. And this goes through, it does basically a grid search. What it does is it tries a bunch of different hyperparameters and see which ones works best, and that helps pick it for tuning. And then it does the fit based on that, and it tells you what the best parameters are. If we look down here at the bottom, you can see this, right? That it shows you for random forest, which is the best algorithm, what the best parameters are. Again, Claude helped me write this code, so this is super helpful, right? If you don't have this kind of logic in there, you basically have to go through and guess yourself. This is a lot of times what data engineers used to do, right? But you can now do it for yourself, and it tells you what the best area under the curve is and CV score. So, what are the interpretations? Uh, again, you don't need to know this, but this is just kind of for your information. Uh, if you have questions about hyperparameter tuning for a particular algorithm, um, ask an LLM. It can give you a good primer on it. So when we say max depth none, it means trees can grow as deep as they need, right? This is good for complex patterns. Uh, the min samples, each leaf node has 2 samples. This is how it breaks the data up when it looks at it. Min sample splits and estimators. These are all things where it says I need 5 instances to split a node into yes, no. And the estimators, the forest contains how many decision trees. Uh, and this is for, we need to balance enough trees for stable predictions and not so many for unnecessary computation. So basically what this said is anything beyond 100 trees was minimal improvement. And this can take some time, which is why I'm not going to run it in class here. So there was a slight improvement. And again, this is because of the data set. Before we tuned it, there was 97, 98% area under the curve, which is still fantastic. So if you think back to an example that we had earlier, where we had an area under the curve that was less than 0.5, this would be something where you could possibly tune that and get that up greater than 0.5, right? And remember, we're looking for 0.7 is good. So, and then after we had a better area under the curve, like 2%, 99.84%, almost 100%. So 2% absolute improvement is substantial in ML. And, that's the kind of stuff that you want to look for. So there are alternate strategies. One thing is interesting that I didn't include in this lab because I don't know much about it is there is a thing called AutoML. Uh, I'll post a link for it, but basically it's up on GitHub, and they have an automated tuning framework that works with scikit-learn. And I'm going to play with that a little bit more. I'll get you some more information about it. I just kind of stumbled on it, but it gives you less control because you aren't training each individual hyperparameter, but it's faster results, so you don't have to go through this whole process. And if you're going to move this to production, some of the considerations would be, computational resources, right? Is it fast enough? to predict and be useful, do you have enough memory? 100 trees is a lot of memory, right? I know it cratered a couple times when I was playing with it. And then, you got to make sure that you save all this stuff. So you got to balance tuning against performance, right? Is it take longer to tune, and are you getting a smaller gain for performance? Um, figure out what parameters you tune first if time was limited. Ask your LLM. It will do a whole guide for parameter tuning for you for particular algorithms. And then, also think about how do you prevent overfitting, right? Because we have a potential overfitting issue here. That could be a problem with dimensionality. So if you're doing feature engineering, or you use like one hot encoder, you can end up with a lot more features. So you have to be cognizant of that. All right, so the tuning results here contribute to our overall performance. Again, it's um, it's too good, right? You're never going to probably see performance like this, but that's because of the size of our data set. And that's intentional, but you need to be aware of that, right? So if we did this with a different file, I let's see. So I did this with a lot bigger file, like 10 times the size. And um, let's take a look at Jupyter Lab. And you can see the results look a lot different, right? So this still has, you see the proportions are reversed. This still has a large sample of malware. Um, you know, this is a machine, just to look. I don't want to dig too deep in this, but I found some interesting things as I was going through this, where I would get features that would dominate. This is kind of like malware, not malware, where might want to filter this out, but you still need to be able to correlate it back. Um, you know, Same kind of results with respect to feature correlation. You can see this is a little bit clearer with respect to the correlation. Um, we have, the number of features is smaller, so we don't have 15, we're only using 10. This too has a scarily good uh, model performance comparison. Again, this is an unusually large percentage of malware, but this is more realistic, right? Because this is a larger sample and it's not optimized as much for training. And this is what I kind of struggled with when I was putting this together is, um, what we should focus on. All right. Right. So, okay. So what are the results and what's the key insight, right? So we started out with a data set with 19,611 samples, right? Those are the rows. 74% of it was malware, 25% was benign. And we had 69 features, right? And this is all stuff that you can tease out through the analysis that we've done so far. With respect to the models and performance, we found that random forest was best, gradient boosting was next. SVM was good, but it wasn't. It was, and again, these percentages, like 1 or 2%, is a big deal. The difference between random forest and gradient boosting is not as significant. But if you look at like that 4 percentage point between SVM and random forest, there's no question which algorithm is the best. And logistic regression was the worst. So, if this was to be believed as to how accurate it was, this would be better than any commercial solution probably available, which is not realistic, right? That 99.7%. is really super good. So if you wanted to, gradient boosting again, that's another tree-based ensemble method that's good for tabular data, right? So that's 99.4%, which is super high, and SVM and logistic regression are much less, right? Commercially, an antivirus, they say 85 to 92% detection rates. Endpoint solutions have 88 to 95% area under the curve, right? Independent testing says that. So, our super duper scikit-learn based malware detector does pretty good. Um, if this was a real thing, I mean, if this was real research, right, it would be a high percentage of published studies. So again, these are somewhat questionable, but again, we're stacking the deck in our favor for the purposes of being able to provide an example. And but you can still do this analysis and see what's going on in your environment, right? If you have access to some of these files, right? It statistically was significant because we had 20,000 samples. Um, Obviously there's hundreds of thousands, if not millions, of these flying around the internet every day that people are analyzing. So they're training their model with more data. So that's useful. Uh, we had consistent results across multiple splits. Um, we had almost 4,000 test samples, right? So that was a fairly robust evaluation. And the results were statistically significant, at least based on what we got. So, um, why are the results good, right? Well, we kind of cheated and we got a PE file that was already set up for us, right? That captures the malware pattern. So this would be more of a needle in the haystack exercise. If you're a 1 to 5% malware, you would need, uh, exponentially more data to come up with these same training results, right? So there's going to be significantly more effort. Um, you know, One thing that we learned from this is that tree-based methods are great with structured cybersecurity data. We also got to make sure we follow proper methodology, right? The 80-20 train test split to prevent overfitting. And then, using systemic methods to optimize hyperparameter tuning. This is super important. So, as you're doing your capstone project and doing the homework, right, think about that, right? Ask your LLM, how can I add code that'll optimize hyperparameters? You may not have to. I've been pretty lucky so far that most of these that I've done, Claude has been pretty good about doing hyperparameter tuning for me. When I do them by myself, it's a lot harder. So I appreciate the LLM assistance and putting these examples together. Uh, and then, your domain expertise, right? If you look at something and you think it is not right, then you have to kind of go back to it, right? The case I was talking about earlier, where when I looked at this, it didn't catch my eye at first, but this had inverted benign with malware, right? So you have to understand what all these different things mean to make sure they make sense. Um, this drives me crazy because the sizing is off and labels aren't clear and things like that. So I would go back and forth with LLM until I got that kind of stuff sorted. But again, this is all stuff that you should be able to uh, achieve, using an LLM to help you write the code. All right. So what are the key findings? What did we learn? Right? The best performing model was random forest. The data set shows that clear class imbalance, right? That's when we talk about class imbalance, this is what we're talking about. This is not normal. You don't have 74% malware anywhere ever. If you do, you should just run away as fast as you can. That's you don't want to be there. Right? The PE header features are highly discriminative. If you want to know more about PE files, I shared a document that talks about them earlier in the chat. I think it's up in the resources on GitHub. If not, I'll load it. You know, the correlation tells us that section entropy and size features are important indicators. And then that there's characteristics that differ, like import table between malware and benign files. So what are the recommendations, right? Ensemble methods are better for production employment, right? Because it is a synthesis of a bunch of different methods. You don't have to run a bunch of parallel models. Make sure that your confusion matrix statistics remain solid and your precision and recall are consistent. Malware is going to change, right? What features are important. If that changes, that might be an indicator that things are shifting with respect to the samples you're seeing. And then you've got to retrain the model on a regular basis with new samples, right? If you start seeing your evidence of degradation of your model, like increase in malware infestation or something like that, you should take a look at your model. And consider additional features like NLP processing for string patterns or behavioral analysis, right? We'll be talking about those a little bit later in future class. All right. I think we talked about hyperparameter tuning already. So there's some stuff here in the homework that talks about this. And sorry, we're running out of time as usual. So you can do a little bit of exploration of this on your own. Again, typically when I have used LLM generated code, it gets pretty close with hyperparameters, but you will need to mess with them a little bit, right? And remember that you're looking at performance versus interpretability. Do you understand it? Accuracy versus speed. And make sure you use your domain knowledge with respect to feature engineering, and that you're looking at things like ensemble methods. Auto ML, right, can help you with hyperparameter tuning. And by doing feature engineering, you can improve the accuracy, right? So if you see a high correlation between features, maybe you'd want to create a feature that has a ratio. So there's a lot to talk about. All right, so let's wrap this up, right? What we've talked about here is static versus dynamic analysis, right? Understanding what the difference between those is. Feature engineering, right? We can create our new features. It's like adding a column in a spreadsheet, right? If I came here to the end and I had a ratio between a couple of my existing features, if I add it here, that is feature engineering. Labeling like malware here in BB, right? That's been added in by somebody. That's not a PE file characteristic, but that's an engineered feature. So, it's like adding a formula column in a spreadsheet is exactly feature engineering. And comparing the models, right? See which one works better. Ask your LLM to give you some visualizations. Make sure you understand what precision, recall, area under the curve, and confusion matrix means, right? And then what do we do for hyperparameter tuning? That's optimization for production ready models. Not so much important while you are experimenting with scikit. But if you get to a situation where you have some code that gets generated and it takes a long time to run, ask your LLM why, right? Say, hey, I'm running SVM and it's taking a long time to run. Why is that? The hyperparameters may be incorrect. We talked about the data set, right? Almost 20,000 samples and 69 features. Uh, we're working towards having a pipeline in the future. What we're going to do is we're going to take these trained models, we're going to save them, and we're going to put them in a pipeline that is going to run end to end and find malware based on these files, right? We should be able to feed it different files that aren't from our sample, and it's going to find the malware. And so we're getting close, right? This is, we've imported the data, we've processed it, we've cleaned it up, we know a little bit about feature engineering, we have the ability to feed it to a model. And again, this is all stuff that you should be asking your LLM to do, right? One thing I did run across that was kind of interesting is I had Claude push back a couple of times. I mean, because it says I ethically can't do anything with malware. So if you run into one of those things while you're using your LLM, try asking it a different question. I had an interesting thing because it wouldn't take my code, but if I copied the code and pasted it into the chat, it would work with it. So you might run into some of those ethical boundaries with some of this. That's part of the game, is learning how to work through those. So if you run into issues, let me know in chat or email, and I'll get back to you. Okay, all right. So what are the limitations? Malware authors can target your ML detection, right? That they figure out where that margin is, and they'll work in it, and that's basically how they evade ML algorithms. They can do polymorphic malware that changes its appearance while it maintains functionality. This is used to defeat signature-based systems, but ultimately when it executes, they all act kind of the same. So you can find them with those methods. Uh, concept drift, right? Malware is going to change over time. This is why you got to keep retraining your models and, kind of going from there. There's a bunch of resources like Ember, that was from Elastic. They put the Ember data set together. Um, and I've got some of these posted, so you'll be able to take a look at them. All right, and then we've got our assignment. Just a second, Tutu, I'll get to you. So we want to be able to visualize our features using Seaborn. So that's this view here. This is a Seaborn plot that shows us features. And then relating the labeled data to outliers. How does that relate to training a model and detection unlabeled samples? So I posted all that. And basically we're doing feature engineering to feed to our model. All right, Tutu, your question?
Yes, hi. So with everything that you just taught us today and presented in today's class, how can we relate it now to, because this looks like data science, more like data science, how can we relate it to the team, for example, a day in the life of a data science, and as it relates to data sets being hosted, whether it's using the cloud system like AWS or Azure? I guess my question is, when you were working as a data scientist, were the systems hosted on a cloud environment? Which cloud environment or cloud platform did you work with? Were the data extracted from?
Okay, I think that's a good question,
Yeah,
and I
because
think
some of us have a little bit of cybersecurity, and
Mhm.
sometimes it's mixed and intertwined with cloud security
Yep,
as well.
absolutely. So think of it this way: is I have systems generate telemetry like logs. Logs go into a sink someplace, and they sit there with all of their myriad features. So much like we have the this malware data set that has a bunch of features, right, that we're not going to use. If you looked at a Windows log, it has a bunch of stuff that you don't want to use. So what you need to do is you need to have a pipeline that takes all the respective data and performs the stuff that we're talking about here, which is data cleaning and pre-processing and scaling and encoding and stuff like that. And what you want to do is from the different sources of telemetry that you have, you want that to feed into a pipeline that processes it so that only the relevant, uh, important features are passed on to your machine learning algorithm. So what you're doing is you leave that data that you've collected, that telemetry, you leave it in place because you might need that for forensics or legal purposes or, compliance reasons, right? I know everybody's got log retention guidelines and stuff like that, but you want to leave that stuff where it is unprocessed. And this is a lot like with the SIM, right? That you're trickling data in. But instead of like a sim where I'm sending full logs in and trying to do analysis, my machine learning pipeline only takes the important features and processes them and sends them on to my algorithm. So you have a separate um, data lake that has that processed telemetry that you use for machine learning, right? So it's a separate store. Where can that be? That can be anywhere, right? It could be in a blob in Azure or AWS or Google Cloud. So looking across all those different clouds, which I have worked in because I think I've worked at all those companies. Yes, I have. So what we always did is we had the interesting telemetry for certain things. For instance, if it was user behavior, it might be logs about data transfer and authentication. I find the specific features through doing the analysis that we're talking about doing here that I want to import. So I'm only sending those into my machine learning data lake. Does that make sense?
Yes, it makes sense. And can you relate that in terms of the team members that you'll be working with, and how do you work with other team members? How is information passed on? Are you working with other
That's
what type of engineers, roles, job
yeah.
title?
You see, this is a really interesting question you're asking because what is happening is a lot of companies are saying, "Oh, we don't need all these people anymore. You need to be able to fish for yourself, right?" But you're going to need the ability to get the data, right? Can you serve this data yourself? You may not have to serve it for production, but you should be able to connect to a data source. So again, there's a myriad of different ways. One, for instance, for the purposes of these demonstrations, I had to figure out a way to take JSON PE files and turn them into CSVs so we could do these demonstrations, right? So that's the kind of stuff where you can use an LLM. So for instance, I asked the LLM, "Hey, can you go and tell me how to get a file from the Ember data set and turn it from JSON into CSV so I can do some analysis?" That's That's this thing right here, right? So this I literally went, and it's a different notebook, but to get to the CSV file here, the malware data for AICS test set CSV, I actually extracted that from JSON using another notebook. So I guess what I'm telling you is, if you don't want to have to track down a data engineer, and you don't want to have to track down a data scientist, and you don't want to have to track down a bunch of other people, you can actually do a lot of this yourself with the LLM, right? As long as you have access to the root data. So this is one thing where there's probably a lot of varied experience in the class with respect to being able to access and interpret the raw data. Raw data is a journey, right? This is kind of process, but you've seen this all before with respect to raw data. We're going to be looking at some Windows logs later, and everybody knows how much fun it is to go through Windows logs. Um, it, I spend a lot of time just staring at data and trying to understand it, right? And doing queries and trying to grok what's in the data and what might be important when I start doing this analysis. So I think that's one thing. That's part of interpretability and explainability
So are you
is
saying in
it,
real life? Are you saying that you are actually working by yourself in real life? You're doing
I
entire pre-processing.
I've
Go
been
ahead.
doing, yeah, I understand your question. I do most of this myself. So I go right to the data source, and I will do the SQL queries, and I will look at the data, and then I will figure out how to extract it and stuff like that. But that's because I've been doing this for 40 years, right? So um, the if you don't know what data you're looking for, um, that's probably your first challenge. And um, it, so think about what problem you're trying to solve, right? And make sure that that's documented. And then what data sources are associated with that? Do you have data? So you might have to ask, um, you know, one of your security team who's responsible for telemetry. So there's probably somebody on your security team that knows how all that raw data goes into data storage and where it is, and can help you get access to it, right? But it is a skill that I would highly recommend that everybody uh, get familiar with, right? You should know how to do enough SQL to be able to do just some basic queries and access data sources, right? So that's the first thing, is you need to figure out what data is relevant to the problem I'm going to solve and where is it. And then once you figure out what data you at least you think is relevant and where it is, then you have to get access to
Can
it,
you
right?
show us that? Show us how to do that, like for like an entry level, at least an entry to mid level.
I'll put something together for a future lab. I didn't think about that, but this but for the purposes of our discussion here, um, I'll share the chat. But I literally went and said, "Hey, I want to go look at a particular data set and import it and change it from like a Windows log format to CSV." So I don't know if I've got it in here or if it's in examples. Um,
And so, what are the systems that you've worked with again? I know you worked at Amazon, so I'm sure you're familiar with AWS,
yeah,
cloud platforms.
AWS, GCP, Azure. I've worked at all three companies, and I have a lot of experience with all of those. But it's just doing stuff like this. It is, I asked the LLM to build this notebook, right? And actually I think I downloaded this particular piece of it, but I have a converter now that can convert event log files to JSON files. And I also think somewhere I've got another converter, um, like this one for NLP, pulls it from JSON. So So you just have to, I mean, figure out where the data is and what format it is that you're looking for. I mean, it's a good question, um, and I don't have an example right off the top of my head, but I'll put one together because that I think that's a that's a great question, right? Is what skills do you need? I mean, I don't even know what skills I have sometimes, right? But
Yeah.
I
Because
end
some
up,
of yeah,
it's just like, oh, I just do stuff, but so I need to think about that a little bit.
yeah.
But it is a
For
good
the
question.
ones who are transitioning in careers, I mean, some people may be transitioning into data science on an entry or to mid level. We don't have, a background in data science just yet. Maybe we're transitioning from security to data science. You know what I mean?
Yeah.
Like,
And that's I think it's a good point though, Tutu, because um we're all transitioning from the thing we were to something to what we're going to be next. And I think especially in security, the tide has changed. That the traditional, and I am a CISSP, so I'm not talking down to CISSPs, but a lot of times that gets used as a pejorative term, right? Oh, you're doing it the CISSP way, where essentially I don't get down into the details, but I talk about frameworks and things like that. But when you get down to the down and dirty data part of it, you're you're trying to learn more about it. So I'll try and put something together for that. I may actually refactor one of the lessons to talk about that some more. But that is, I mean, it's part art and part science. I think some of it is knowing where to look. Um, I got my start doing like Windows log analysis, and it sort of branched out from there. But being able to get the log sources and use them, I think, is a useful skill. The question of which log sources to use, that's a whole different ballgame, and I think that relates back to the problem you're going to solve. So if the problem is, this is a real world example, not as big a problem as it used to be, but a lot of times admins, when they run PowerShell, they'll run encoded PowerShell because it's easier to get script stuff to run inside a coded PowerShell than it is to actually put it in the PowerShell code itself. So TLDR is that adversaries do that same thing as well. So if I had to figure out, I want to look for encoded PowerShell and see what percentage of it is in there and how it relates to potentially malicious commands, I have to know about Windows logs, right? So what do I need to know about Windows logs? And that's probably a whole course in and of itself. But what I'll try and do is lend some flavor to it and talk about how do we get data and how do we figure out what data we need to solve a problem. And I'll adapt one of the lessons to talk about that. I mean, it's a great question. I could talk up for 2 more hours about it, and I'm sure everybody here is getting tired of listening to me, but I'll adapt one of the future lessons to talk about that, but because it is a good question, right? Again, part art, part science. You need to know the science. Then the art is your domain expertise, which is why AI is never going to replace us, because we have the ability to go through and look at things in a way that AI can't. But an LLM is your friend because, for instance, uh, try asking your question to LLM. What knowledge do I need to have to, get information from Windows logs or some data source, right? How do I get service logs from Azure, right? Those are the kinds of questions you can ask, but you have to think about it in a context of a problem you're solving. So that's sort of back to some of the initial stuff we discussed. All right, long answer, light on specifics, but I understand what you're asking me, and I will try and weave that into a future lesson. All right. Okay, we are way over. I'm sorry for those of you who have hung with me. I appreciate it. And if you got questions about the homework, ask them. Again, I am realistic about deadlines. We have a deadline, but it's not a deadline. As long as you get your work turned in, it's still going to count. And, by all means ask. We're getting into kind of the meat of this. So you might run into some frustrating things. But again, the LLM is your friend. If you run into issues, ask, right? Ask your LLM, ask me, and I'm going to ask my LLM. Maybe I just ask the questions better. I don't know, but I'm happy to help you get answers. So uh, that's kind of it. All right. Thanks for hanging. I'll see you all on Thursday. I am, I'll try and catch up on messages here after we log off, and let me know directly if you got any other